last week it was like, oh, you want to stream Discord right now, right? That's what you want to do. Nope. All right, so we were talking about basically using the strength of, or basically using the molecular structure of an acid to determine the strength of an acid, at least relatively speaking. Which things can we look at in a Lewis structure to make predictions about how strong one acid is compared to another acid? So the big things for binary acids were polarity and strength of the bond between the hydrogen and the anion. So more polar bonds are going to be stronger acids, bless you, and weaker bonds are going to be stronger acids. So the more we polarize the bond, the more that the anion has more of the electrons, more likely it is that hydrogen gets picked up by something else because it's going to be electron deficient. Bond strength matters too, and actually the big determiner for bond strength is atom size, so the size of the anion. As the anion gets larger, it means that the hydrogen and the anion are farther apart, which means that the bond is weaker. Which is why even though the most polar out of these is hydrofluoric acid, right, fluorine's super electronegative, so that's going to be a really polar bond. Because there's a really strong bond, because fluorine is so small, the hydrogen and the fluorine are very close together, so it's actually a weak acid. Whereas as we move down, we get decreasing strength because they get larger. Decreasing bond strength. So those are the strong acids. Now, oxyacids, and this really makes the polyatomic acids make sense, especially the oxyacids. Again, there's sort of the electronegativity of Y, or whatever the central atom is. As that gets more electronegative, so iodine's being the least electronegative here, chlorine being the highest electronegativity, the Ka increases, which means that it's a stronger acid. And that's because when I have a stronger or a more electronegative atom in the center, it's going to be stealing more electronegativity or electron density from the oxygen, which is going to make the bond between the oxygen and the hydrogen weaker. So just like binary acids, weaker bond means stronger acid. So mostly some trends. The other one is the number of oxygen atoms bonded to Y. So whatever our central atom is, the more oxygens it has, the stronger the acid. And there's a couple things at play there. One of them is that all of those oxygens, pretty electronegative, so they're going to be pulling electron density away from the central atom and away from hydrogens. What do you think the other reason is? This might be a stretch. This might be more of an OChem question. I think Lewis structures. So one of the reasons is, what I'm saying is, more oxygens means that this is a stronger acid. I said one of the reasons is electronegativity of all those oxygens. They're pulling a lot of electron density. What's another reason that having more oxygens would weaken the bond between oxygen and the hydrogen?
Does it have to do with double bonding?
It does have to do with double bonding. Resonance structures. The more oxygens you have, the more resonance structures you can have. So like comparing, I mean, this has no resonance structures. This has no resonance structures. Maybe kind of, but they're not going to be equivalent. When I get to 3, now I could have, well, actually, no. Here, if we remove the hydrogen, I guess that's the important thing. If I remove the hydrogen, the anion is this, which now has resonance. So that negative charge, after losing the hydrogen, gets distributed between both of these oxygens. And up here, when I've got 3 oxygens, my Lewis structure would be this for the anion, which now I'm sharing that negative charge across 3 different oxygens. And the more that you can spread out a charge, the more stable that it is. So this bond is weaker because without that hydrogen, this molecule is stabilized by sharing that negative charge. And so the more oxygens that you add, the more resonance structures you can have. Because if we go up to this one, now that negative charge is shared between all 4 oxygens. So that's something that becomes super important in Chem is whenever you can share charges across multiple atoms, that makes it something that's more stable. And it's more likely to exist in that form, or more, I guess, energetically beneficial to exist in that stabilized form than in another form that's not stabilized. All right. So which of these is more acidic? Hmm? Why A? More oxygens. Yeah. So like a basic answer would be there are more oxygens. A deeper answer would be that when I remove this hydrogen, I have now the negative charge here, which gives me a resonance structure with the other oxygen, which is going to be more stable. So the bond is weaker. Cool. All right, one more definition of acids. One that we're not going to spend a ton of time on, but one that would be useful if you're taking organic chemistry. So the Lewis definition of acids tries to encompass more things as acids and bases. And so like in their first, the Arrhenius definition of acids and bases was the most limited. It says it has to have hydrogens or it has to have hydroxides and bring those to the water. The Bronsted-Lowry definition, which we've been using most of the time, has said, change that. And it basically says, okay, well, maybe it doesn't have to bring the hydroxides, but it just has to increase the hydroxide concentration by taking hydrogens from water to make hydroxide. Our acids still kind of brought protons, or at least shared protons, hydrogens. The Lewis definition basically cuts this back a little bit more and now is no longer focused on just hydrogens and donating or accepting hydrogens, but it's lone pairs of electrons. And so you really need to have at least an idea of, or you have to have a mental model of Lewis structures or know what the Lewis structure is or draw out a Lewis structure for a molecule to try and figure out if it has lone pairs that it can donate or places where it can accept lone pairs. So our acids are now electron pair acceptors, and our bases are electron pair donors. Which is the part of this that I never really liked is that the other acid-base models, at least, it was usually like donate a proton. And that was the acid. But now it's donate an electron pair, and that's a base. The definitions, though, make more sense if you think about it from, well, if you think about ammonia as your model for why this definition works. So ammonia in the Bronsted-Lowry definition is a base. And to try and keep that consistent, That's why it's a base in the Lewis definition. Because now my base here is what has this lone pair of electrons that it donates to the hydrogen. So hydrogen is still very much an acid, or at least part of the acid definition here. But because it's an electron pair acceptor, there's not enough room for that. I'm going to draw arrows. So ammonia is the electron pair donor. So you can take this new definition and apply it to lots of things, even things that we couldn't apply it to before. So because we're no longer focused on hydrogen and now it's about donating or accepting lone pairs of electrons, our acids or bases don't even need to have hydrogens. So like boron tetrafluoride, BF3, which is one of the ones with a weird Lewis structure because it doesn't have a completed octet on boron. Boron and aluminum can both be fine with just 6 electrons, which makes them both really good Lewis bases. Wait, Lewis acids. See, even I got it backwards. They're really good Lewis acids because they can still accept a lone pair of electrons because they could complete that octet, but they don't have to. So my NH3, which has a lone pair, donates the lone pair to the boron, which makes this the Lewis base, and this is the Lewis acid. So when you draw out a Lewis structure to try and figure out what is the Lewis acid and what is the Lewis base, you're looking for anything that doesn't have a completed octet or can be rearranged to accept an electron pair. This is where a lot of our complexes come from. So I said aluminum is another one that, like boron, happy without an octet, but can still react and accept a lone pair of electrons. So here again, ammonia donating to the aluminum, forming that adduct bond. It's not exactly a bond. Oxygen is a good Lewis base because it's always got a couple lone pairs. It can donate those to boron. Or we can have things that rearrange to create space. So CO2 can do that. Just want to write this outside of all of the arrows and stuff. Right, if we just focus on like CO2 by itself, are there any empty spots for electrons? Not really. The carbon's already got 4 bonds. The oxygens each have 2 bonds and 2 lone pairs, so everything's got octets. Which is why things have to rearrange a little bit in order to turn into carbonic acid. So in the Lewis base is our water, donates a lone pair to the carbon. That lone pair pushes a pair of electrons out of this double bond and up onto the oxygen, which would give oxygen a negative charge. And partly because of the geometry of the way these things arrange, that oxygen then can act like a Lewis base. And then the hydrogen is a Lewis acid. These electrons come down here to this oxygen, and now I form a new bond between that top oxygen on carbonate and the hydrogen. So by shuffling all of these electrons around, I can get to a compound that doesn't have any formal charges and form carbonic acid. This is actually the reaction that's happening if you're doing an acid-base titration and you like breathe into the flask, or if you just leave it for long enough, it's pulling CO2 out of the air. The CO2 is reacting with the water just like this to form carbonic acid, which then lowers the pH and it'll fade. If you're using phenolphthalein, it'll fade from pink to clear. This also kind of explains why things like aluminum or small, highly charged cations will act like acids when they're in water because they form lots of these adducts. They react with a bunch of waters. And then that water will eventually, like if there's another step here, we'd get Al H2 5 OH plus and H plus. So technically, any cation in water can act as a Lewis acid, but the small, highly charged ions especially will end up making the solution acidic. So just as a like, where does any of this show up in nature? So just like CO2 can react with water to form carbonic acid. Carbonic acid is a relatively weak acid. I think they said, is it in here in the slides? Yeah. The pH like of water droplets or rain that's saturated with CO2 has a pH of a 5.6, which is a little bit acidic, but not too bad. Like lemons are like 2, very acidic. But sulfur dioxide and nitrogen dioxide, which are both combustion products, or both come out of like gasoline as like trace elements and trace impurities, but also especially burning coal. These get thrown up into the atmosphere and they can react in a very similar way to carbonic acid to form much stronger acids in the rainwater, which I remember this being a big scary thing, and then now it just doesn't, it's not a thing anymore because we regulated it. But nitric and sulfuric acids can make the pH fall down to 4.3, which even though that seems like not very much, it's 20 times more acidic. And that can start to not only damage like buildings, or here like these limestone statues have been eaten away because limestone is calcium carbonate. So calcium carbonate will dissolve in acid. So bridges, anything that's made out of limestone will start to dissolve. It can also accumulate in lakes and rivers where it decreases the pH. That can also cause, if you've got really a lot of really acidic rain for a long time, can dissolve limestone and create sinkholes. But also just having a lower pH changes the balance of soil, so it'll strip out nutrients. Things that aren't normally soluble at closer to neutral pHs become soluble at lower pHs. And as those things dissolve, they then get washed out by the water, carried into rivers, and so it strips the soil of its nutrients and kills trees or other plants. Similar to ozone, though, this is one of those things where we're like, hey, this is a bad thing and we can do something about it, so we should do something about it. And so regulations put in place to lower SO2 emissions. This is why cars have catalytic converters. I'm not sure exactly what they did specifically for coal-fired power plants, but we have decreased the SO2 in the air over time so that acid rain is not something that we really have to worry about. It is one of those things, though, if we stop regulating it, then it will become a problem again. It's not like it's just gone and we never have to worry about it. Although I think, we're getting rid of coal-fired power plants. So that's like one of the main problematic sources. Yeah. So regardless of what you think about the government, I'm not talking about current government, but the government in general, there's some things that have been good, especially those protecting the environment. that we share. Otherwise, you get situations like, I don't know if you guys know how the Ohio River used to catch on fire. Yeah, like the whole river would be on fire multiple times. Why? Because chemical plants would just yeet their waste into the river. It was like, all right, it'll carry it away. And it did, but it also killed everything in the river. It meant that there was so much oil and sludge on the surface of the river that it would catch on fire. And that's why we need some regulation. Because otherwise, they just make it somebody else's problem. When I say they, I mean companies. Okay, so I typed up this very basic recap. There's the lecture slide stuff. But just to talk through some of the things that we've gone through in this chapter, because I was thinking about it and it's like, what have we even covered? So we talked about the Arrhenius definition of acids and bases. I don't care about that all that much. Don't spend too much time on that. It's a single line. We talked about the Bronsted-Lowry definition of acids and bases. That you should know because that kind of determines how you do a lot of the other math. So most everything was based on Bronsted-Lowry definitions. This is one that I actually typed out some equations for. So acid/base, anywhere that there's like acid/base, the chapter breaks it up. We talk about acids first, and then you talk about bases. But really, those are two parallel things that are like same but opposite. So acid-base strength as it relates to Ka and Kb. So you have a Ka equation, which is related to sort of a generic equation of an acid reacts with water, produces H3O plus, A minus. And that's also how we get Ka, which is just the equilibrium expression for that equation. So anything that makes Ka a larger number increases the H3O plus, makes it a stronger acid. And then it's the same thing with bases, really. But for bases, we have actually a different equation. As much as we think of acids and bases as being opposites, they're not exactly opposites. So you can't just take the inverse of Ka to get Kb, because when we talk about Kb, it's a different equation, slightly. So here I have a base reacts with water. I get OH minus, and then my conjugate acid of the base. And so our Kb expression is just then, oh, that's supposed to be OH minus. OH minus times the conjugate acid divided by the concentration of the base. So again, higher Kb means a stronger base or a more basic solution, which would also be a higher P, or a lower pOH. Again, thought it was important to reemphasize that like Ka and Kb are not inversely related. We talked in the last chapter about how if you reverse an equation, then you just inverse the K value. Can't do that for acids and bases because they're based on different expressions. And where that really becomes important is like later in the chapter where we talked about like how does the like the conjugate acid or the conjugate base of things, how did those affect the pH of a solution? We calculated some of those. And that was that whole section where I went like I did too many examples, basically, and we had to cross some of them out. So a lot of the times you will be given a Ka for an acid. You might need, though, the Kb. So if the acid is this expression, again, general expression, the Kb for that conjugate base of the acid, so this is the conjugate base for the same expression. I did mostly take this and reverse it. Now I've got A minus here, HA on that side, but this is A minus reacting with water. Where over here it would be A minus reacting with H3O plus. So these are different expressions. They get different values, but they're both related through, or I guess when I add them up together, what I get is the autoionization expression for water. So water reacts with water, gives you H3O plus OH minus. So really, it's like this, right? Add those expressions together. If I add those two equations, chemical equations together, then that's going to be Ka times Kb. And because these two equations added together gives me the expression for water, then they equal Kw. So if you want to find Kb for the conjugate base, you use this expression of Ka times Kb equals Kw. Kw is always 10 to the minus 14. We also talked about calculating pH and pOH, negative logs. Should be able to do those. Using ice tables to calculate H3O plus for weak acids and bases. So just like I add a weak acid, I add a weak base, what's the pH or pOH going to be? We talked about percent ionization. And the weird fact that, well, the kind of weird fact, when you do the math, it makes sense. Percent ionization decreases with increasing weak acid concentration. Same thing for bases. So the more of a weak acid that you add, the lower its percent ionization is. The amount of H3O plus will also go up. So weak acid concentration increases, H3O plus concentration increases. The percentage, though, is what decreases. Diminishing returns. Oh yeah, calculating pH and pOH. If you have a strong acid and a weak acid, or a strong base and a weak base, essentially the strong one wins. You almost don't have to consider the weak one. Or if you have two weak acids and bases where you have to compare Kas, compare Kbs, calculate for the stronger one first, then calculate for the weaker one. And then I guess this stuff should have gone down here, but I also think it's fine. This was the whole section about like, if I have the conjugate acid or the conjugate base, is that going to act like a weak acid or a weak base? So if it's the conjugate of a weak acid or a weak base, it will act like a weak acid or base itself. If it's the conjugate of a strong acid or base, then it won't. And then the other thing for these was the small highly charged cations can act as weak acids because they form a complex with water that ends up essentially kicking out a hydrogen. And then we talked about polyprotic acids, which polyprotic acids is kind of like having two weak acids together because the first ionization suppresses the second ionization. So you basically only need to calculate for the first one. The one exception was dilute solutions of sulfuric acid, H2SO4, because in its first ionization, it's strong, but the second ionization is weak. And the reason it's for dilute is because it's like adding a tiny amount of strong acid and then adding weak acid. So you get a little bit from the strong acid and then a little bit more from the weak acid. Do you have a question? Thought I saw a hand. And then the kind of the stuff that we just talked about today and on Friday, determining acid strength for molecular structure. So things like more polar bonds means a stronger acid. Weaker bonds means a stronger acid. Larger anion size means weaker bond. So larger anions will be stronger acids. More oxygens are stronger acids, and more electronegative central atom in those polyatomics especially is a stronger acid. So I would use this as a guide for kinds of problems to look for either in the slides or in the book or in the Alex problems and like match them up with these concepts as practice. This is like the outline, and I'm leaving it up to you to fill in the gaps for problems to put in there. It will be. Yeah. I will post it. We'll have to correct that OH minus. That didn't take very much time at all. Did I even... Any questions? Okay. Then let's start the next chapter.